Okay, Chem students, I think this is the last little tutorial that you need out of Unit 6, Section B. The other things you should have already looked at was how to represent particles in an ionic compound, and then how to look at a particle model and represent or be able to label whether it's an element, molecule, ionic, and so on. This last little bit is some additional information that some of you already had about dot diagrams. And so I have a periodic table here, and I'm going to give you some information of some patterns that show up on the periodic table, and you might find it helpful to add these to your periodic table. Again, like we normally do, we're going to ignore these transition metals because there's variability that happens in there. So we're just going to talk about the distinct patterns that occur. We're going to talk about outer electrons because it is the outer electrons that either share electrons with something else to form a molecule in a molecular compound, or transfer electrons to something to be ionized, to have a positive negative charge in order to form that attraction that occurs in an ionic bond. And so if we just focus in on the outer electrons, group 1, first column, well, guess what? They have one outer electron. All right, so I'm going to label that 1. That means it has one outer electron. Because these are metals, they tend to lose electrons, and that means that the charge that all of these have, in addition, is a +1 charge. Again, maybe that's something you want to add. But these numbers I'm representing now are electrons. Group 2, second column, well, they have 2 outer electrons. And again, they're metals, they tend to lose electrons when they form ions. They lose 2, which means all of these have a +2 charge. We're going to skip all of these, and so the next column I'm going to label, the third column, which is known as group 3, and these are all the A group, 3A. Guess what? It has 3 outer electrons. All of these, when forming ions, tend to have a +4 charge, or +3 charge, excuse me. Guess what the next column is? 4 outer electrons. These guys have 5 outer electrons, then 6, then 7, then 8. Now, this column is kind of important because 8 outer electrons is the maximum that you can have no matter what kind of atom you are. There's no more room in your very outside level than 8. And if you want more information about how that can be, how can an atom have, like this one for example, has 35 electrons. How can it be that it only has 7 in its outer level, and that no matter where you're at on this periodic table you can have more than 8? Come see me and I'll try to give you some more background about it. But at this time it's really not necessary unless you're interested, and I'd be happy to do that. The thing about this being full, these are known as the noble gases. They are inert, which means they're not reactive. They do not need to form compounds to be as stable, because they're already as stable as they can be all by themselves. Okay, the other thing I'm going to add that you might want to add to your periodic table is how to represent these outer electrons. And so what I'm going to do is, for each of these, above each of these columns I just talked about, I'm going to draw an X. And that means it represents any of these in this column. Since these guys have one outer electron, here's what their dot diagram would look like. One dot on any side of this symbol. So what happens is, like for example, let me actually draw hydrogen's dot diagram. This H tells us what element it is. It represents the nucleus of hydrogen, and all of the electrons except the outermost, which I'm going to specify with a dot. There is one outer electron. So this is the electron dot diagram of hydrogen. Again, the symbol tells you what element it is. It represents the nucleus, all of what we call the inner electrons, and here's the outermost electron. This is the exact same thing you would draw for all of these. You would just change the symbol. And so that's why I have an X here to represent any of them in this column, one dot on the outside. The other thing about dot diagrams is you have to visualize a box around the symbol that you write. These represent the possible outer orbitals which are in the outermost level. And the maximum that you can have on each side of this box is 2, and that's because only 2 electrons can occupy each of these 4 possible outer orbitals. So let me draw what the symbol would look like for all of these. Same thing, I'm going to draw an X. And when they form a compound, they have two outer electrons, of course, because they're in the second column, but one will be here and one will be here. They try to spread out as far as possible because electrons are the same charge, and so they don't want to be next to each other. Then I'm going to skip these. Here is group 3A, has three outer electrons. Here's how they arrange themselves when they form compounds. Next one, 4 outer electrons. Here is how they are arranged when forming compounds. Okay, I'm going to put the next one up here just to give me some more room. Here is all of the symbols for this group. These guys have 5 outer electrons. So electrons will spread out and occupy an orbital all by themselves if they can. But because this group has 5, one of these is going to need a pair. And it does not matter where it is, because these are three-dimensional and we can turn them and look at them any angle we want, but one side needs a pair, 3 singles to get us to 5. Okay, now I'm going to put this one right here. This time I need 6. So again, we're going to put 4, and then this time we need 2 of them that have pairs. So this is the dot diagram for all of these. 2, 4, 6. Okay, now I'm on this one. I'm going to put it up here for the sake of space. And so I need a total of 7. 1, 2, 3, 4, 5, 6, 7. Oopsie, I don't know what just happened. I guess I zoomed in. Okay, there's the dot diagram for that one. And here's the last one. Really big. Guess what? It has 8. All of these are filled. No more room for any. Again, they are inert, noble gases. Okay, I'm going to try to zoom back out because I don't know how I even did that. Guess I'm going to press escape and I'm going to probably lose. Oh no, there we go. Excellent. I lost all my pictures, but hopefully you wrote those down or pause it or go back and do that. Okay, I want to quickly do an example of how we're going to use this. And if you need more examples, there's going to be a practice associated with this, then you can check your answers. So I'm going to take a compound, very common one, sodium chloride, and draw what the dot diagram of that compound would look like. So I know I have Na, and I have Cl. Oh, I zoomed again. Okay, that's all right. I'll keep it. All right. Na is from group 1. So remember, it has 1 outer electron. Chlorine has 7 because it's from group 7A. So there is 1 orbital that sodium is lacking an electron, 1 orbital that chlorine is lacking an electron, and that's where a transfer will occur so that they are more stable to form their compound. So here's what that would look like. Here is sodium's 1 electron, and then just for the sake of this, here's chlorine's 1 outer electron, and then it has orbitals where there are pairs. So this in blue would be the same dot symbol that you drew above group 7A. This in red, with the red dot, would be what you drew for group 1A. This is what it would look like together. And again, normally we don't specify different colors. I just wanted to see how that works out. The place where there are single electrons in orbital is where that transfer will occur to form this particular ionic bond. So that's the type of thing that you're going to practice with dot diagrams, being able to put together where the outer electrons will go to form those compounds. So check out that practice, do some of them, do all of them, check your answers, get help as needed. Enjoy.